past 3 p.m. in Beijing and 10:30 in Moscow. Let's begin our seminar. Today is our pleasure and a great honor to have Professor Vassily Manturov from the Moscow Institute of Physics and Technology give a talk. He is the organizer of our seminar and he has contributed a lot to the seminar. Today he will talk about virtual knot methods in classical topology. Let's welcome Professor Vassily Manturov.
Thank you very much. It's a great honor and a great pleasure of mine to give this talk here. And I'm very happy that Professor Yao attends our seminar. I'm going to talk about some methods which appeared in knot theory, methods which allow one to construct picture-valued invariants and invariants in free groups and other objects which were first invented for virtual knots, and now I'm going to discover them step by step in the case of knot theory and classical topology. And today I will give the whole review of the whole theory and several methods which appear here, and I will present a general plan of the whole construction. After that, I will concentrate on one specific result, which is related to so-called free knots. And then I will say how to construct some invariants of free knots valued in free groups. Free groups, well, if we have invariants which are valued in free groups, these invariants are powerful enough because free groups, well, they are very much non-commutative. And on the other hand, it is easy to compare because in free groups, word problem and conjugacy problem are easily solvable. So now I'm going to pass to the notion of a free knot. And actually, I start with the notion of frame for graph. So this graph naturally appear in knot theory. All knot projections on the plane are graphs of regular four graphs. And also I want to require that at each vertex I have four edges and they're split according to the opposite relation. So here, when I draw something on the plane, opposite edges are drawn opposite. So now I also want to say what the unicursal component of a free graph. Well, this is just what we can draw without, so if we take a pen, so we can draw something on the plane without moving the pen. So we always go transversally and we finish drawing one component. After that, we go transversally from an edge to another, to an opposite edge and draw the other component and so on. Okay, and now I want to define the notion of a free link and a free knot. So these are just equivalence classes of these framed four-valent graphs, a modular abstract Reidemeister moves. So actually, when we have usual knots, we draw them on the plane, and we have three types of moves, known Reidemeister moves, and all knot theory is based on Reidemeister moves. And actually, here I want to make the situation more abstract. In fact, we can say, okay, some situations of the corresponding codimension happen, so we can pass to formal objects. So what do I want to do? So first of all, I would like to forget about over-under information for knots. So at each crossing, I do not indicate who is over and who is under. And on the other hand, I want to allow arbitrary framed four-valent graphs. So this means I don't require any planarity. So if I was just forgetting the planarity, and if I stayed with this over and under information, I will get to what is called virtual knot theory. But free knots, on one hand, they have a lot to do with virtual knot theory, and on the other case, they are much simpler because we don't have this over under information. And in this talk, I want to prove that there are some very nice free group valued invariants of free nodes. So this is the general plan of what I'm going to do, not only today, but actually of the whole program of what we are going to do with our seminar. And actually, I assume we have classical nodes. In fact, we can do not only classical nodes, but some other objects, which should, first of all, be one-dimensional. And on the other hand, these objects should somehow be related to Reidemeister moves. I'm not going to unravel the details of the first three points of my general plan. So I'm just saying about the general scheme what we can do. So we can map classical nodes to links. Well, links are some objects which can have more, I would say, reference points. So if we have yet another component, then we can get something like, for example, linking number for free or something like that. Then having knots or links, we can get knots in the second cylinder, something like this. So here we have something like homology. So S1, unlike just the three space, has a lot of has at least first non-trivial homology groups. Then we can map something to free knots in various ways, and then the fourth step is how to construct many picture-valued invariants and many free groups invariants. One of the general principles of our today's work and our further work is to make all invariants non-commutative. So roughly speaking, we can say as follows. Assume we have an invariant of some topological object. And this invariant can be thought of, say, we consider a moduli spaces, and then we just try to find some homology class and some cohomology class. And if their dimensions fit nicely, then we can say, okay, some intersections just give us a collection of points and we count them with proper signs. So actually many invariants can be thought of this way. And now I want to argue that in some situations, we can count them not in a commutative way. I would say a plus b minus a minus b equals 0. But we can try to count them in a non-commutative way, in the sense that we can have, say, a times b times a to the minus 1 times b to the minus 1 is not equal to 0. So for example, for three component links, we can have, say, linking numbers pairwise being 0, but the Milnor invariants to be non-trivial if we have some commutators. And I want to, so, and one of the general problems and one of the general objectives of our program is how to construct non-commutative mathematics everywhere. So non-commutative things go together with picture value things. So in some sense, we can do the following. We can consider, and of course here I would, before passing to the concrete examples and other things, I would like to ask I would like to thank many people for discussing this with me. And so first of all, I'm extremely grateful to Kim Samjon and Kim Surach who helped me preparing this talk. So this is one of the main tools of our further study. So this main tool is called the parity. Well, we can assume that we have some discrete collection of objects to count. So this can be crossings of a node diagram, or they can be some elements of some zero-dimensional modular space. Or we can look at some solutions of some PDEs if these solutions form a zero-dimensional modular space. We can look at intersections of manifolds. We can evaluate some classes, and we do many other discrete things. So I want to discriminate between even ones and odd ones. Again, this will be very much detailed for the case of free knots, and for the general case, well, just try to imagine the following. If we have some homology or even Z2 homology, so then we often get parity. So we often can evaluate some Z2 homology class and say, okay, this, say, crossing is even and that crossing is odd. Or this thing is even and that crossing is odd. Well, it is well known that virtual knots very often behave like classical links. And what do I mean by that? Well, by that I mean that if we have a virtual knot, then we can discriminate between even crossings and odd crossings, and somehow having even crossings, we can think, okay, those behave like crossings between the component and itself, and odd crossings behave like crossings between two different components. And actually, so people working in knot theory know that for links, it's much easier to construct invariants than for knots. For example, for links, we have linking numbers and further linking numbers and so on. So then actually, for virtual knots, we can apply parity constructions for getting links, and actually more parities, more reference points, more homologies, and so on. And one thing more we can pay into attention is that we can pay attention to is that odd things persist until they are cancelled with similar odd things. So what do I mean by that? Well, assume we want to have an intersection between, say, two manifolds, and we want to count this intersection modulo 2, then it may happen that two intersections of, well, we can say opposite signs, if we count them integrally, or just two neighboring intersections cancel. So then we can say, okay, they cancel, but until they cancel, each of them persists. And somehow there are some disappearing cycles or disappearing intersections, which are trivial in some homology sense, say those which go to cusps. So actually, if something is odd enough, so if something is homologically non-trivial, then it should give rise to parity, and something which doesn't cancel. Okay, and now I want to pass to cats. So what do I mean by cats? Here I want to say some words about the similarity of what's going on in the theory of virtual knots, theory of knots, and theory of free groups. So schematically, we can say the following. We want to deal with free links, and we want to deal with free groups. So having a free group, the word problem can be solved obviously just by canceling until we can canceling whenever possible. So if we have, say, some word and we want to write down a word which is equivalent to the initial one, then the initial one should live inside any word equivalent to that. So the reduced word is somehow the complete invariant of the free group element. And on the other hand, we can say, okay, this invariant is not just some bare count, but this invariant is much more interesting because it's very much non-commutative. And here I just draw schematically what we can do for minimal diagrams of virtual knots, and this works perfectly for virtual knots and free knot theory. We can do the following. So assume we have some locally minimal diagram that we cannot decrease in one step. So this means that all moves we can perform somehow increase its complexity. So assume we want to perform some move. So in knot theory language, say second Rider-Master move. So assume we have this. So here two new crossings get born. And in this new diagram, we can see the initial diagram. Inside, if we just smooth two crossings and we get here, then these two diagrams are identical. And this is very similar to what we are doing with the reduced words and free groups. So actually, one of the goals of the whole program is to construct picture-valued invariants, which are similar to free group invariants. So somehow we can take a collection of something, and this collection is drawn as a picture or written as a free group. And then, for example, if we know that something is valued in a collection of pictures, this gives us much more information about the initial object. Say, having an information that some polynomial has some degree, we can very implicitly get some evidence that our diagrams are very much complicated. But knowing that we have some subwords or some picture inside, we know a lot about all possible diagrams. Actually, I will soon talk about the parity bracket. So this is a formal invariant which is built in a way similar to the state sum. So people often use in low-dimensional topology. So we take a certain summation over crossings or something like that, or some states. But in my case, this summation will give rise not to numbers, not to some abelian groups, but to pictures with coefficients. In order to do that, I should consider the following objects. So they're just Z2 linear combinations of framefold graphs, modular, something very, very similar. So first of all, I want to be lazy. I want to say that I don't like coefficients. I don't like polynomials. And I want to show my main idea as pure as possible. So I want to consider everything modulo Z2. And also my objects are considered modulo Reidemeister 2 moves. So this is an addition or a removal of a bygone. So in fact, objects modulo Reidemeister 2 moves are well, if we do only Reidemeister 2, then it's obvious that the minimal object is unique. And so we can say that objects modulo Reidemeister 2 moves are just like elements of the free group. So actually, we can say that we're dealing with linear combinations of graphs. So now I want to consider the following definition of a diagram. This diagram is a diagram of a free knot, so a frame-coherent graph. Then its parity bracket is defined by the following formula. So we take this graph K, and we take all possible states of this graph. All possible state, what do I mean by state? We take a crossing, and if this crossing is even, then we have two ways to smooth it out. So we can remove it by smoothing it in a horizontal way, or we can remove this crossing by smoothing it in the vertical way. So here are the two ways of smoothing of an even crossing. So possibly I didn't draw it here. So I'm showing it. So does my screen show up? Can you see my screen? Can you see this piece of paper? So I'm just showing now. So the two ways of smoothing of an even crossing. So if you can see it, then I can say, okay, for odd crossings, I do nothing. So this means that if I have odd crossings, then they remain crossings. So this is like the case of free groups when we cancel some letters and we do not do anything to other letters. And actually, if I do something for classical knots, then this is generally not the case. So what I'm going to show now is that some local minimality yields some global minimality. This means that in many situations, if we have an object which cannot be decreased in one term, then it cannot be decreased at all. So for example, this is the case for free groups. So if you have free groups, then we can say, okay, we have a reduced word, then it's locally minimal. hence it's globally minimal. And actually, this is the same for some groups, and this is the same for some types of knots. But this is not the case for classical knots, and this is not the case for arbitrary groups. And now I want to make my theory more virtual and as virtual as possible. And actually, here is possibly the main formula I like the most, the formula that if our diagram has all odd crossings, then the bracket of D is equal to D. So what is meant by that? So I do something to even crossing. I splice them somehow, I smooth them somehow, I reduce them somehow, I do something. And for odd crossings, I don't do anything at all. So this means that if all crossings are odd, I don't do anything at all to the diagram. So this means that my diagram has exactly one state. Actually, the number of states is 2 to the n, where n is the number of even crossings. And if there are no even crossings, then I have just one state. And actually, in this formula, I like very much. So the bracket of D equals D. We have D in the left-hand side, meaning a knot diagram as just one of many diagrams of D. And D in the right-hand side means, well, a concrete graph, well, maybe up to Reidemeister to move, but this is not a great deal. So D in the left-hand side means that we have, well, an object up to many, many different moves. And D in the right-hand side means a very concrete object. So since we have an invariant of our knot, this means that if we do have some D prime equivalent to D, then the bracket of D prime will be equal to D. And this means that D prime will contain D inside. So here is the first non-trivial example found in this way. So here I have an odd diagram. So where all chords are odd. So odd in which sense? Odd in the sense that each chord intersects oddly many chords. This is actually not the case for classical knots, but it gives a lot in virtual knot theory. And here is the corresponding frame for Venn graphs like this. So the Gauss diagram is obtained from this graph if we just consider this as a circle and we connect by chords those points on the circle which have the same image here. And actually the bracket of this knot is equal to this knot itself, and which was the beginning of the free knot theory. So what features do we have here? Possibly the main feature is that if a diagram is complicated enough, then it realizes itself. So this is like the reduced word in the case of free groups. So the reduced word appears in any word equivalent to that. Okay, and so locally minimal diagrams appear to be globally minimal. In fact, here I mentioned this bracket, but since that in virtual knot theory and some other theories, when we have some non-trivial homology, we can find many other brackets which satisfy this property. Bracket of D equals D. Okay. In particular, we found that in the classical algebraic group. So then we have the following features. We can raise y dimension higher, and we try to get some folded disks with singularities. And actually, we can try, for example, to do the following. Assume we have a regular Fock graph, and we want to cap it by a disk. So under some odd circumstances, we can say, okay, if we can cap it by a folded disk, then we can cap it by a disk with just trivial intersections and more or less without any triple points and cusps. And knots with parity behave like links, and we can get a lot for virtual knots. Actually, where to take parities for classical knots? In fact, to do that, and this will be done in further talks, we should look for some homology. And actually, if we have knots in the cylinder, then we have non-trivial homology coming from the homology of the cylinder. And whenever we have some non-trivial condition for the moduli space, some non-trivial Z2 homology class, then we get Z2 homology, and we get some parities for objects we're interested in, some intersection points and so on. So we have, if we have, say, a Legendre non-transverse knot, so well, of course, this is a problem. This is a project just still to investigate, but okay, I'm ready to talk to people about that. So we can look at other things. So what sort of application can we get here? So applications which become immediately for free knots, for virtual knots, and so on. Knot theorists like things like mutations and knot invertibility. So for example, we can invert our knot. So we can invert the orientation and say, okay, are these two knots equivalent? Well, of course, no, if we have that the bracket of K is oriented. Actually, this is not the case for the initial parity bracket, but this works for other parity brackets. So for example, if the bracket of K is equal to K, for some reduced knots, this is like the free groups. So we take a free group and we write down the element in the opposite directions. Of course, if our knot is not a palindrome, then it's not equal to itself written in the opposite direction. And the same for mutations. So if we cut something and paste in some other place, so well, if we know that for the minimal diagram, if it's not equal to itself, then why should it be equal to itself if our bracket of K is equal to K? So we can solve many problems by just looking at one representative of a knot if we have enough odd situations. Also, we can do something for cobordisms. And actually, if we want to estimate something like cobordism genus, we can something for commutator lengths. And actually, if we have some problems, if there are some students or people who want to have problems for research, then I would say that many topological structures give rise to some classes, maybe characteristic classes or some other classes. Then if we have such, we can produce some parity. For example, for complex structures, we can take, okay, so here we have some condition like f equals 0, and here we can say, okay, we have real part of f equals 0. So then we have some real codimension 1, which gives rise to some homology class, and in turn this gives rise to parity. And one more project for maybe further students or further co-authors is to construct Kirby theory. I think there will be many obstacles, but I hope this will give rise to invariants of three manifolds. Okay. Possible further applications, two knots, manifolds with structures. Actually, we initiated something with 1J, but so far we have only one small, quite modest paper. And we can actually study manifolds in higher dimensions, so I don't have much time here to talk about that, but there are some keywords, groups G and K and gamma and K, which can do something. And actually, we can study moduli spaces, and instead of doing something like characteristic classes, I would say that I want to do characteristic loops. So some loops in some non-simply connected moduli spaces, which give rise to some count, which is not a bare count of plus and minus, but which is some very much non-commutative count. Okay, so we want to do some non-commutative mathematics, and maybe here I want to announce some steps which are not yet done. So we can, if we want to do something very much far away, then the general thing is that we want we may try to count these intersections like paths which respect the order. If we are happy enough, then this order can be taken into account. And instead of getting A plus B minus A minus B, we can have A times B times A to the minus 1 times B to the minus 1, which is non-trivial. And actually, this can give rise to some things in groups. And this has a lot to do with G and K groups, Bray groups, which I don't have enough time to talk about. And here I would say, here we can get some things like categorification. And there was a famous joke due to Lou Kaufman when he saw my picture. He said that categorification corresponds to cats. So this means that if we have a crossing or if we have some point, then to this crossing or point or some intersection thing or some other discrete object, we can associate a picture like a cat. And this picture can generally say much more than we can get just from some intersection in homology, which gives us just numbers and not pictorial objects. And actually, well, if we want to categorize something, what do we want to do? Instead of just numbers, we want to have some spaces and of some dimension. So instead of 1, we want to have 1-dimensional space. Instead of 5, we want to have a 5-dimensional space. But well, I would say a cat or a word in a free group gives us much more information than just the number of letters in this word in a free group or the number of crossings of that cat. So we can get a categorification here, but still it's well, something in this relation is done in my works with, I would say, with William Rushford, but again, this is done for virtual nodes. Again, I want to revisit something I started from today. So we want to have a free group. So free nodes are very much similar to free groups. And for free groups, the reductions are just when we cancel A and A to the minus 1. And for free groups, and for free nodes, excuse me, I do the second decrease in Reidemeister move. So I have 2 crossings which are canceled if they are kept by bygone. Of course, this can remind many other situations where the research is not yet initiated. For example, if we have 2 crossings, people can imagine a Whitney disk or something else, or some 2 homology groups, 2 chain groups in the same cell complex, which are canceled by a differential. So these second Reidemeister moves appear everywhere in topology, but any further step can be hard because of some details. And here I want to concentrate myself on some details of a very simple example. Okay, so steps towards the goal can be free nodes to elements of free groups. And then if I have free nodes, then I can get some, so if I don't have a reference points, then I can have elements in some conjugacy classes of a free groups, because if I don't have the reference points, then I should write words down cyclically. So the realization plan for just the rest of today's talk is that we can find some homological condition and investigate something which can be even and then which can be odd. So then we want to construct a certain free group, and I want to do some invariants of free nodes which are valued in free groups. And actually, as a consequence of the invariant I'm going to construct explicitly today is that we have something which is not very much non-commutative. This is not the case for classical nodes. It is well known that classical nodes do commute. Okay, and actually, again, if we have some even objects, we try to associate some generators of a certain group, and these generators can be canceled out if I go along some path and cancel similar objects, so we can have such relation which appears everywhere in every group. But sometimes there is some painful thing which appears in classical knot theory, and that's why the approach I'm talking about today has not been applied to classical knot theory for many decades. And this painful information is that some crossings of knots, not of links, but of knots, may disappear. So in some configuration places, we can have things like cusps. So when some homology class disappears because it's trivial from some higher point of view. For knot theory, we can look at the first Reidemeister move. And if we try to apply some naive group theory, then sometimes we get relations of just generator is equal to 1, which kills the whole group. So that's why it's quite hard to do something for classical knots if we want to do it in a naive way. Okay, we can do something for words, and I want to omit this slide. And actually, again, we want to pass from homology to homotopy, and we want to pass from free abelian groups to free groups. So what do I mean? Well, for example, if we want to intersect, two classes, then when intersecting these two classes, it would be nicer to have these classes to be somehow ordered. So what do I mean? For example, if I have a loop, intersecting something of codimension 1, then I can go along this loop and count something in order. And then instead of just saying A plus B minus A minus B, I can say, okay, I have A times B times A to the minus 1 times B to the minus 1. And potentially, I want to have characteristic loops instead of characteristic classes. Possibly, I can look at some intersections between embedded complexes instead of intersections of immersed complexes instead of intersections of embedded surfaces. And I want to make my mathematics as non-commutative as possible. Okay, so now I want to take some steps for constructing invariants of free knots. And here I want to be as detailed as possible. And so the process will be very clear. And I want to do 3 steps of constructing an invariant. So the first step will be some construction of an integer valued invariance, which is reduced to some bare count. So I will be counting some odd objects. So this can be thought of as a count of some intersections between homology classes. And then, well, actually, this step 1 was discovered by myself when I was trying to study cobordisms of free knots. And actually, this was invented as a sort of invariant which is valued in a free group. No, excuse me, in a group. And this group is, though it is non-commutative, however, this group is commensurable with Z. So actually this invariant, at first glance non-commutative, turned out to be, well, actually valued in some group, and which is commensurable to Z. So it has Z as a, well, actually it turned out to be an invariant valued in integers. So the first step gave rise to some naive bare count, and then I discovered that this invariant can be just a bare count. And the second and the third steps can give rise to invariants which are valued in free groups. So the group which is written here, in the second step is exactly this group, which is commensurable to the free group. So you see, I will draw the calligraph for this group, And the Kelly graph for the group is like that. So you see, so we have generators A, B, and C, and you see that if we draw all elements of that group just here, then we see that this group has as many elements as the infinite dihedral group. So in fact, there is not so much coming from non-commutativity here. And but nevertheless, the step of rewriting just numbers into elements of a group can be quite useful if we want to expand this group. And then I will say how to expand this group to have non-commutative things. And then after doing some more tricks with the group Z2, I will get, well, if saying completely algebraically, it can be a certain skew product with Z2, but I don't want to dwell into algebraic calculations too much. I can just rename letters, rewrite words, and do some tricks in order to get invariants in a some genuine free group. So in some group of exponential growth, and we will see that our invariance will be genuinely non-commutative. So it will not be a bare count. It will be something in a non-commutative group. So here is the plan. And now the first step. Okay, assume we have a Gauss diagram. So this means that we have a circle with a collection of chords. So a circle with a collection of chords gives rise to some framed graph, as we drew here, for example. And on the other hand, we can somehow write this graph as a word. So somehow we can write down a word when we go along the circle, and when we mark endpoints by similar letters. So we should just investigate what sort of letters we should find here. And actually, there are two very nice things which do not appear in classical knot theory, and actually which were known to Carl Friedrich Gauss, and possibly the work of Gauss I'm going to mention now was one of the first works in knot theory ever. So Gauss was trying to draw diagrams of the plane concerning to such diagrams of the circle. So we can try to draw a circle on the plane, and we want this circle to have intersections in just prescribed order. So, for example, we can say, okay, I can draw something on a sheet of paper, and so, for example, we can try to do this chord diagram 1, 2, 1, 2. So this means that we have one crossing here, which I call 1, and then we have one crossing here, which is called 2, and then we get 1 and 2 and get stuck. So please tell me, so Sanjan, can you see the piece of paper I'm now demonstrating? Sanjan, Jayan, can you tell me whether you see the piece of paper I'm just demonstrating here for the camera?
Yes.
Okay, so here it means that if we have this Gauss diagram with two chords and we try to draw it on the plane, then we get stuck. So we can draw this diagram without some third crossing. And actually, I want to draw this crossing and encircle it, which means that when I draw it on the plane, this crossing should not exist, but we cannot do without. So these encircled crossings in the left part of this irreducible odd diagram on the left are just the crossings which do not exist, which should not appear, which do not exist on this diagram on the right, but which do appear if we try to draw on the plane something which is not drawable. And actually, the theorem due to Gauss was that if something is drawable on the plane, then all crossings are even. And actually, Gauss made some mistakes. He thought that this condition was necessary and sufficient, and it was not sufficient. And the first criteria was probably proved 1 century ago, maybe more than 1 century ago, even in 20th century. And he gave a sufficient condition for something to be drawable on the plane, for some graphs to be planar. And in fact, the point where great people make mistakes usually give rise to some great conjectures, like Poincaré, who was thinking about homology and homotopy to be the same. Well, Gauss thought of even and odd crossings, and somehow these diagrams not drawable on the plane gave rise to virtual knot theory. And well, unfortunately, this tells us that we cannot have odd crossings for free for classical knots. Everything is even. So even means so the chord is linked or intersected by evenly many chords, and even and odd means that it is intersected or linked with oddly many chords. And if we look at such a diagram, then we see, okay, if we want to do a Reidemeister 3 move, then the chord doesn't change its parity. What does it mean? That it means that it toggles two adjacently with two chords, so we switch the parity twice. So if something is canceled by Reidemeister 2, then these two things have the same parity. And actually, for Reidemeister 1, we have only even thing. So what we have here for the second point is that actually, if we had only point 2, then we would have something like free group. When we have nothing but a to the minus 1 equals 1. So if we were happy to do without 0.1 or 0.3, we would be happy to get just invariant valued and free knots. And so 0.4 is the theorem due to Gauss. And so we would be happy to do without 0.1 and 0.3. And actually, the parity bracket is a tool which allows us to get maps from objects modulo 1, 2, and 3, Reidemeister 1, Reidemeister 2, and Reidemeister 3, though here 1 and 3 are switched, so possibly 1 should be 1 and 1 should be 3 and 3 should be 1, excuse me. So if we were able to do only with the Reidemeister 2, then we would get invariance valued in free graphs. So now we have to choose how to call even things and how to call odd things. And now the main principle is as follows. Allow me to use letters A and B, and allow me to make some distinction between various sorts of B. Here I want to apologize for two words I'm using here. The words are type and sort. In fact, I want to do the following. So first of all, I want to stretch out my diagram on the circle to make a diagram on the line. So instead of just chords which connect points on the circle, I want to have arcs connecting points on the line. Okay, so I want to have some reference point, and the objects I'm going to study here will be not just free knots, but what I call long free knots. So this means that I want some cutting point. Well, I don't want to touch the cutting point. Of course, if we have something like groups, we can get some group valued invariants, and when we pass from long objects to compact objects, we can say, okay, this element undergoes something like conjugation. And if we are happy to have something valued in free groups, then of course we know not only what the word problem is, but we also know what the conjugacy problem is. So, okay, allow me to look at even chords or even arcs, and even means intersects evenly many chords. And allow me to draw them in red. And the other things will be, so the even ones are A's and odd ones are B's. And now I want to make a distinction between sorts, types, etc. of B, and they will be as follows. So first of all, I want to say, okay, an odd chord, it intersects oddly many other chords, right? So among these chords, there can be evenly many even chords, or there can be oddly many even chords. So this makes a distinction between what is called B and B prime. And actually, there is some further distinction. One distinction is needed in order to make some group-like formalism. So for groups, I want to have some relations like AB equals B prime A. So for group-like formalism, I want to make a distinction between B and B prime. And there is some other formalism which can be thought of as a bare count formalism. So in some sense, the four black chords I have here can be thought of as chords of the same type. Well, again, excuse me, type, sort, and something else, I would say that they should be the chords of the same sort, excuse me, though they are of different types. So actually, here, in order to say that a chord has a certain type, I should take into account two bits of information. One bit of information is how many even chords it's linked with, and the other bit of information is when I write it down as a word. So what are the positions of this chord? So is it started in an odd position, or is it started in an even position? So though this B and B prime are B and B prime, so one has a prime and the other does not, they are counted differently because they are counted, the same for the bare count, because one of them has even ends and the other one has odd ends. So allow me to formulate the main theorem for the bare count, which was the first theorem is in that direction. So actually, I want to count these B's and B primes with respect to the sort. And actually, this will be an invariant of long free knots. And this will be an invariant of free knots up to sign. Why up to sign? Well, because if we want to have compact things, then odd objects will remain odd, but the initial point can get changed, and this will switch the sign. So actually, the initial point can switch the sign and make objects with plus to be objects with minus. And actually, if we want to prove this theorem, we can create a word. And if we create a word, we can get something which gives rise to some objects, to some words in generators of the group. And these words are up to relations, and these relations turn out to be A equals 1, B equals 1, B prime equals 1, and also AB is equal to B prime A, and AB prime equals BA. Actually, if there are students here, they can make these exercises and see that whenever we apply Reidemeister moves, we have exactly these relations. So in fact, this can be written down by using the Kelly graph of the group in question. And the Kelly graph here is as follows. So we have two horizontal lines with a B and B prime, and we have vertical, I would say, rails. So we can say we have a railroad, we have A vertical. And our relations are as follows. If we go up and down, we return to the initial position. So A squared equals 1. Analogously, B squared equals 1 and B prime is equal to 1. But if we want to go B prime, then we go 2 steps to the right. And B prime to the n is very much non-trivial. However, if we are stuck to that railroad, so the invariants we can get will be just integer numbers, or possibly integer numbers, possibly even integer numbers. So here, the red path here from the unit corresponds to the example I drew here. So we can have BA, 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 and so on. So here we have this, and we see that our invariance corresponds to 8 steps to the right. So this is A, and actually this means that the knot is non-trivial. And even more, it says that this free knot cannot be kept by a disk with singularities. So the coordinate class of this free knot is non-trivial. However, it's proved long ago, and I don't want to pay much attention to that. What I want to do just now is to say some words how we can have a genuinely non-commutative group. And actually, to this end, I want to get rid of the relations B squared equals 1 and B prime squared equals 1. And I can do it again by manipulating some even and odd conditions. So actually, here is some group I have. So here my generators are A, B, and B prime. Again, exercise for students, draw accurately the Kelly graph of this group and make sure that this group is has exponential growth. And looking at this group, you can have various non-trivial invariants. Well, it's enough to see that this group has some subgroup isomorphic to Z times to the free group of rank 2. Okay, so this is the group, and here is the rule for writing down a word which will give rise to an invariant value in this group. So we had a rule how to construct a word in our group phi of k. And now the new word will be called C of k. And so I want to manipulate a bit with odd things, and I want to replace B prime in even position with B prime to the -1, and replace B in even positions with B to the -1. Now let's look what's going on if we apply Reidemeister moves. So for Reidemeister move 1, both endpoints correspond to the letter A. A is even, okay? So then we have just A squared equals 1, and this relation still persists here, okay? And now, if we have, say, the second Reidemeister move, we can have 2 even chords. Then there is no problem because we have 2 cancellations of A squared equals 1. There is no problem at all. Or we can have some nice things like trivial relations, because, well, if we have B and B prime, actually B and B prime cannot appear in the second Reidemeister moves. The 2 adjacent letters for the second Reidemeister move should have prime both, or should be without primes both. So again, as we had in G, so here we had relations like b squared equals 1. But in this situation, the rule for our plus and minus signs is just the rule which prescribes one of those two b's to have -1. This means that instead of just b equals 1, we will have b to the -1 equals 1. And also we can check all other moves and see that we get rid of those relations square equals 1 to be 1. And this means that we get to this group. This group, and this group is truly non-commutative. And if we want to make, if we want to look at the example we gave before, we see that here we have some very non-trivial word. So what's the moral of this example? The moral of this example is that whenever we have some non-trivial objects, and whenever we have some odd objects, we may try to arrange something like non-commutative count. So non-commutative count, or something valued in non-commutative groups, or something like that. However, there are two caveats which made this project longer than one could expect. And these two caveats are as follows. So first of all, sometimes it's not very easy to find characteristic cycles. So if we have, say, some configuration space, well, sometimes if we want to find some one-dimensional objects, which many people can say, okay, it's a common knowledge how to find one-dimensional characteristic classes, whatever. But sometimes one-dimensional characteristic classes are realized not by a circle, but they're realized by a collection of circles. This means that our circle splits into something, and instead of just free knots, we can have something like cobordisms of free knots. And actually, when we have cobordisms, well, we have letters, and we can separate these letters from one another, and it's harder to take account of the order of letters. So this is one caveat, and the other caveat is that sometimes we have trivial cycles, and find something truly odd is hard enough. So okay, and now just some words about this example. For when the bare count gave us bb prime to the 4, which gives us some 2 points at length 8, and the non-commutative case gave us some highly non-trivial word. Okay, now I want to say that if we stay with free knots, then more or less for free we get non-invertibility of free knots. So, which means that if we have some word, we can write it in the opposite direction, and some word which is non-palindrome gives us an answer to that question. And any sorts of mutations, and actually we can get non-commutativity of free knots, which is not the case in the classical knot theory, because in the classical knot theory, well, we know that knots do commute. And it's known that virtual knots almost never commute. And I think this can be, this will be the case for free knots. And in order to finish that, actually we have to be accurate, because incidentally some invariants can turn out to be the same. But I think that they never commute, except for some obvious situations when we have j to the m and j to the n. So when their powers of the same. Actually, further situation when we can enhance, in fact, the groups constructed here can be enhanced if we have some other situations, like some other bits of information. For example, for virtual knots, we have over and under crossings, which can which can give us some indices for b to the -1, and so on. So actually, we can have even larger groups with more indices, more generators, and we get more invariants. This invariant is a sliceness abstraction, so we can get cobordisms of free knots here, and we can upgrade many things for virtual knots, and we can get more invariants. And as for classical knots and knot invariants, they will be considered separately. And actually, further problems which can be saved by using, which can be solved by using this approach is that actually one more problem which allows one to be, which can be solved by using parity methods is that if we have even objects and they're equivalent, then they're equivalent in the even category. For example, if two classical knots are equivalent as virtual knots, then they're equivalent as classical knots. The same for braids. And more or less, this is because we can have something called parity projection. So actually, in this situation, we can prove that some maps in groups are injections, or some maps between topological objects form some maps between categories. So they are also inclusions because there is a projection to invariant to the initial object. So for example, like classical knots are a part of virtual knots. And now I want to pass to some further objects. Then we can say, okay, sometimes an object is bad if it's not drawable on the plane. So this means that if we have some, say, virtual knot, then it's non-classical, or some Gauss diagram is not a Gauss diagram of some classical object or some curve on the surface, because something is not drawable on the plane. And the obstruction to that non-drawability is the abstraction to this non-drawability. Sandra, please show the list of references. I think, okay, here is the list of, okay. The abstraction can be because of some homology class. So in fact, we can try to prove that whatever abstractions to some embeddings or other things we can have, they should originate from some Z2 abstractions or some non-drawability. And there should be some projection maps to from general objects to some easy objects, like virtual knots mapped to classical knots. And this is yet another object of further research. Now I want to mention some papers here. So the first paper, free group invariants of free knots, is the brand new paper I just posted onto the archive on December the 21st of the last year. So this is about this examples and these invariants I told in more detail today. And also parity was introduced more than 10 years ago, and we have these things in some journals. In some journals, so we use parity for getting invariants of free knots and invariants of cobordism of free knots. And in fact, now we have a book called Invariants and Pictures. Let me see. Yeah, so here is the book. So here I told a lot about invariants of various objects and how they are similar to groups. Now I want to finish my talk by mentioning a couple of questions Professor Yao asked me about. And these are the following two questions. So one of those is how to study Calabi-Yau manifolds and further symmetry and so on. In fact, having whatever sort of manifold, we can try to figure out whether we have some odd objects, whether we have some parity conditions. And if we have, say, if we have, for example, if we have, for example, a complex structure in a certain manifold, then we can look for some codimension one surfaces, hypersurfaces, which come from some complex structure and something like real part of something is equal to 0. So this work where we started studying complex surfaces was initiated with Wang Jian. So it was an initial step for when we have some structure, we can try to get some parity, and then we can try to get some non-commutative groups and so on. But this was just an initial step. And the second question was about whether we can do some trivalent graphs, whether we can have some trivalent graphs somewhere. Can we get more constructions like knots? So I told a lot in detail about free knots, and free knots may have some further indices about over/under information, or maybe corresponding to some information which comes from some homology classes and so on. And of course, if we have an object more complicated than a circle, for example, a theta graph, then having this theta graph, we can have some intersections between different parts of the theta graph drawn on a plane or on a surface. And these intersection graphs can give us something modular 2, or even maybe integral, I don't know. But this is my vision about some further steps towards studying these objects. Of course, it requires much more time, and I hope that in some reasonable time we will be able to give more talks and to tell more about classical knots and possibly some higher dimensional manifolds and some other problems in topology. Again, having higher dimensional manifolds, we may try to look at configuration spaces, which can be made non-simply connected, and having something non-simply connected, we can try to find braids or maybe other objects which give rise to non-commutative groups, and non-commutative groups can be studied by using parity methods I'm mentioning. Okay, so thank you very much. So this is the time where I'm going to stop.
Thank you very much. Any questions or comments?
Yeah, Vassily?
Yes.
Yeah, okay, great. Yeah, I think it's a very nice project. As I mentioned to you that there's some potential connections with the homotopy theory, and so I say a bit more. There are some part, as you said, about the, like a free group is okay, about the reduced word, how to understand the structure of reduced word. This is exactly we want to know a long time and related to the higher homotopy group of spheres. So the combinatorial descriptions were reduced to the some properties, how to get understand of the reduced word in free group for some special type of like a Brownian type of words. So that's one potential. I think you have asked the concrete question. Well, let's of course in low dimensional cases we know how to compute, but as I said, for general case, this is a very open problem in homotopy theory about the general.
Thank you very much for your. Yeah, thank you very much for. Thank you very much for your question. And here I would like to mention that braids are much easier to work with than knots, because for braids we have a collection of points, and the number of points in each section always stays the same. And this is a very important feature. So for knots, we have to overcome much more obstacles. But I think that for higher dimensional manifolds and structures like vibrations and other things, more or less we can arrange braids. So for example, whenever we have a linear complex, relation, then, excuse me, a linear complex fiber bundle, then, for example, in C1, which is R2, we can consider the some dynamics and points mean braids. So we have some braid groups and we have non-simply connected spaces, and these non-simply connected spaces can be used for studying relations, for studying vector bundles. So potentially we can study not only homotopy groups of spheres, but we can potentially study vector bundles.
That's good. Well, okay, so maybe let me say a few. Actually, I will be particularly interested for the correspondence of the diagrams and words, right? You mentioned like this words, you can make a diagram. This is a give geometric description for the words for the groups. So there's some type of words. Actually, you get a collection of diagrams. So they will give a new approach to study. I would say try to think about the potential application over there. That's one part. Another part, as you mentioned several ways. So actually, you use the fringed graph. This is very good. So use fringed graph. There is a way to go to homotopy theory to go to the just simplicial groups. The way actually we did is just simply when you get a fring, we can make a simply naive cabling along the fring, so you will produce simplicial group in such a way, and all these operations become to be a simplicial map. That means you use a totally different approach to study homotopy theory for loop space.
Yes, and actually, I think whenever we have some further structure, for example, for me, I was mostly working with cobordisms. I would be happy that we can get cobordisms on invariants. So what do I mean? Well, if we have just some bare count of some 5 and 3 and 2, well, it's hard to imagine how 5 can be mapped to 3. And if we have objects like free groups, well, then we can see that in free groups we can have something like splitting a word and then pasting words, and this is related to something like commutator length. And again, if we have some structures like simplicial groups, we can try to figure out what it should be for groups, and I think there should be many more structures.
Yeah. Well, when we have a simplicial group, already provide a lot of invariants for the knots. Say they have some high dimensional structures invariant. You take some quotient groups and take some even homology, you get totally different invariants. So there will be, if you understand the homotopy type, you can create a lot of new invariants out of that. And if you combine together, I think it will be possible to get a new type of invariance.
I want to have invariants of homotopy type were evaluated in free groups. So that's what I want to have.
Okay, great. Yeah.
Thank you very much.
Okay, thank you.
I have a question.
Yes, please.
Free links are related to the group Gn2, and three free links are related to the group Gn3. Can we construct the K-free links such that the relations are exactly the relations for Gn_k, the group Gn_k? I think we can choose K in K index in from the n1 to n set, and consider the k minus 1 tuples of the k index, and there are k such k minus 1 tuples. Then we can similarly construct the k-free links.
Okay, so thank you very much for the question. The answer is that if we have braids, if we have just one-dimensional braids, so usual standard braids, we have GN4. We have GN4 for looking at points, at 4 points on the plane which belong to the same circle or maybe line. As for higher GNK, for larger K, for just one-dimensional braids, it's a nice question which is related to algebraic geometry of curves of some genera. So we can look at algebraic curves which pass through a collection of points, of some points, and again it should be some beginning of some relation between G and K and algebraic geometry. Actually, for braids, G and K for higher K originate from braids in some higher configuration spaces, not in R3 and not necessarily one-dimensional. So there are such examples, but again, there is a very subtle difference between braids and knots. So in fact, for GN2, it's more or less easy to close up braids to get knots. And for G and K, we should take care of cobordisms. So this means that if we want to have invariants of the initial objects, which are valued in braids, and we want to close it up, we should take care about the moves which appear in the target space. And sometimes these are moves you have seen here or have seen in my previous talks. And sometimes we can also have moves like saddle moves, which can split one circle into many circles. And these are moves which should be which require some special care. So again, for braids, everything is easy. And for knots and links, it's more complicated. That's why it took much more time for me to study knots and links rather than braids. So that's my answer.
Thank you. I have another question. For the K3 surface, it is hyperkähler, so we can consider the special Lagrangian submanifolds in the K3 surface. And there are 3 of them. So I think we can consider the intersection of the special Lagrangian submanifolds, and maybe they are related to the GNK group.
Well, I think, so what we did in our initial paper, I would say this was a very first step. And this step was a very modest because we were restricted to some very partial case. But what I would say is that the more structures we have, the more canonical hypersurfaces, canonical classes, and other objects we have. And if we have a hypersurface, this allows us to make further distinction between types of intersection points. So for example, here we can say that we have B and B prime, and there we can say that we have B red and B green. So we will have much more powerful groups, but we should see where these green and red things can come from. In fact, the general approach can be like that. We can try to take some homology, which we know for sure, which is invariant under something like cobordisms or whatever, and try to make our crossings or double lines or some triple points, whatever, to have more information from homology. The more we can, the better. And then we should try to thread this collection of our points into some double line, which would be always one-dimensional and which would be subject to some moves which are not cobordisms, but just moves like Reidemeister moves. And then we would be able to take care of the order. And then we would be able to write groups, modular relations, or free knots, or whatever similar objects. So we take our labels from homology, and then we want to arrange our objects to be as homotopy, as I would say characteristic loop, not characteristic class, but just characteristic loop passing through these things.
Oh, Vassily, can I ask one more question?
Yeah, sure.
Yeah, still I wonder from my point of view, so I'm interested in this part. You see, if for GNK or this flint knot, you mentioned the clavier, so would be the geometric structure helps to understand the structures of these diagrams, or the part I try to get some fundamental connections, and possibly we need more from the geometry to collect. I don't care if it's more complex, okay, but if it's a fundamental connection, then we can reduce the question. You know, homotopy group is invariant. It's not like global ones. They need to catch some kind of global invariance to reduce to another object. So would the geometric structure helps, like yeah.
I hope so. I hope so because whenever we have structures, so here what I have in my mind and what gives me more hope that we can get lot is that we can consider two structures. One of them is the complex structure we studied with Wang. The other one is Legendre knot structure. When we say okay, we can say okay, we can consider say not say 3 points on one line, but say 3 points which belong to a line from some family, or 4 points on the plane from some family. So if we have something like contact or simplicial or something else, we can have families of lines, families of planes, and some other things. So then we can try to find some collection of something which is of codimension 1. And more or less, my objects is as follows. If we can find something of codimension 1 and of general position, which turns out to be odd, I mean, which does not disappear from some obvious point of view, like Reidemeister 1 and knot theory, then this will give us a new parity or a new color or a new distinction between generators. So I have two evidences why it should work for more structure. So one of them is complex and the other one is Legendrian. And Legendrian is related to contour structure, so I can expect that if there are Keller or Calabi-Yau or more, then we can use some interplay between different structures, which can
Yes.
give rise to more generators, I would say.
Okay. Yeah. Oh, great. Thank you. Yeah.
Thank you very much for your questions.
Yeah. Thanks.
Vassily, I have a question.
Yes.
Yeah. So in your slides, you show us the conclusion about the invertibility of the links. So what about the empirical reality?
Well, you know, so far I did not. So far I was talking about classical, about non-classical links, but virtual. Well, actually, more or less for virtual knots, more or less for free. So if we have bracket of k equals k, then okay, we should also make some distinctions, say early overcrossing, late overcrossing, and make some distinction between early and late. So, for example, if we have bracket of k equals k, and say k tilde is the k tilde is the inverse image, is the inverse, or not inverse, mirror image, then the bracket of k tilde equals k tilde. And if k is not equal to k tilde, then for one representative, then we have this for knots. So for virtual knots is more or less very cheap. And for classical knots, well, it will be a subject of another story and of another talk. So for virtual knots, yes, it's easy and cheap.
Oh, okay.
And for classical knots, well, the key thing is to find parity.
Oh, okay, I see. Okay, thank you.
Thank you very much.
Any more questions? Let us thank Professor Manturov again.
Thank you very much for coming. It was a really